Okay, so this is gradually getting harder because we're adding more and more tests and types of series and things to memorize, right? So, and that's going to continue. So there's kind of two parts to this. You have to memorize the facts about different kinds of series and sequences. You've got to have the memorization side down, but then you have to have the understanding side down too. When you see these complex expressions and symbols, you have to know what they mean, and you have to make connections and make conclusions. So it's both. It's memorization, lots of memorization, but understanding what's going on too. In order for the success to happen, you've got to have both of those. Okay? So last time we left off, we were looking at we looked at the comparison test. Did I start it? Yes. So what did we say? We said if you've got a series that you're trying to say AI is the series we have, and we know another series BI that's divergent, and all the terms of BI are less than the terms of ours, AI. Then what could we conclude about ours? Also divergent, right? So you've got this thing that you're trying to figure out, and you have an idea that it's divergent. Well, there's another series, all of whose terms are smaller than the one you're looking at. And you know that one diverges. Then you conclude that yours diverges too. If it's all the terms are bigger, then the sum is going to be bigger, and bigger than a divergent series has to be divergent, right? And then on the flip side of that, the one that you are looking at, you have a hunch that it converges, and there's another one you know for sure converges, and all the terms of that one are greater than ours, the one we're looking at. Then wouldn't it make sense that ours converges too? Right? Because when you sum up your terms, they're going to sum up to something less than one that you know converges. So then you can conclude that yours converges. So that's the idea of the comparison test. Okay? So we did this example last time. What did we compare this to? So we looked at this sequence, and we said all these terms are... So first of all, do we suspect that converges or diverges? Converges. Because all the terms of this thing are less than what? 1 over I cubed, which we know is a convergent p-series, right? Since that's a convergent p-series, and all of these terms are less than those, this one definitely converges too. It's going to be a smaller sum than one that we know converges. Okay, another example. So we've got 3 over square root of I minus 2I cubed, and maybe a good first step would be to write out those as exponents. So 3 over I to the 1/2 minus 2 times I to the 1/3. So what kind of series, or what do we suspect about this one? Convergent or divergent? Why do you suspect divergent? I'll give you a hint. What's that? That's a p-series. So is that a divergent or a convergent p-series? Divergent, because the p is less than 1. Or actually less than or equal to 1, right? If it's 1, it's the harmonic, diverges. Less than 1 is even worse, right? Diverges. So now what do we have? Now we're going to subtract off a positive number from the denominator. So what's that going to make that whole fraction compared to what I circled in red? I'm making the denominator smaller. Makes the whole fraction bigger. So the whole fraction is bigger than the series that I circled in red. And the series I circled in red was, what was that? Diverges, right? So what about ours? Diverges because it's even bigger, right? So all the terms are even bigger than the divergent series, the p series, 3 over 1 to the I to the 1/2. Does that make sense? So we're comparing it to one we have to a divergent series. And so as you listen to me talk through that example, you see that you both have to have the facts memorized, but then you have to reason through this. You have to say, oh, if I subtract from the denominator, it makes my denominator bigger. No, it makes my denominator smaller, so my whole fraction is bigger. So this is comparison. We're comparing it to this divergent p series. Questions on that one? Okay, what about this? What do we see in here? You see something like a geometric. So is it in the form of geometric? Is this a geometric series? This, exactly the one I'm giving you, is it geometric? What is the form of a geometric series? A r to the I minus 1. Is that what you have? Do you have a r to the j minus 1? Why not? Because of this j right here. This j, it's no longer geometric because that j is in there. That's not part of a geometric series. But the rest of it is, right? The rest of it is. So let's actually turn the rest of it into a geometric series. Now 2 to the 3j, we need something to the j, or to the j minus 1. So what is that the same as? 2 to the 3j is the same as what to the j? It's like 2 to the 3 to the j, which is 8 to the j. So that's what that denominator becomes. And then I have 5 to the j minus 1. But we need, so what is our r value going to be? 5/8. But in order to get it correct, we need what? So we're going to have 5/8 to the j minus 1. So we also need another 1/8, right? We need another 1/8 because we just lost one of our 8s. We got one less 8 here than here. So we need another 8. Now we've got j8s in the denominator, right? Okay? And so, but then we also have this 1 over j. Okay, so that's now we kind of carved out the part that's geometric and got it looking exactly geometric. Notice 5/2. What? 5/2 is greater than 1. But we didn't really have 5/2. We really had 5/8 because it was 2 to the 3j. So now 5/8. So what about this geometric series? Converges or diverges? Converges. Okay, Ben, I need help with smartphones and laptops, please, when you get a chance. This converges, right? Because 5/8 is less than 1. And what are we doing? We're multiplying by 1 over j. Does this whole thing converge or diverge? So we've got this is converges. And what does multiplying by 1 over j do to a number? What does multiplying by 1 over a number do to the number? Get bigger or smaller? Smaller, right? You're taking a fraction of it, right? You're going to take 1/2, 1/3, 1/4. So we've got a convergent. We've got terms that converge. And now when we multiply 1 over j, we're making all those terms smaller. Conclusion? By the comparison test. This thing converges by comparison to this geometric series because all the terms of this are smaller than all the terms of this series. Because you keep taking a smaller and smaller fraction of what you had before, which was small enough already, right? So by comparison, that thing converges. Questions on that one? Yeah?
How did you figure out that the geometric part converges without doing a full
No, a over 1.
That's what converges to.
So that gives you the value if it converges. The question of converges or not comes first. And then if it converges, then you find out what it converges to. So how do we know that it converges? That comes first. The R is between -1 and 1. R is between -1 and 1. Now, because there's this 1 over j here, we have no idea what this sums to, because we just lost. It's not a geometric series anymore, and we have totally different terms, so we don't know what it sums to. But we can conclude that it converges. How about this one? Okay. So we make a hypothesis. Do you think this converges or diverges? Why? Can we do comparison to 1 over 3k to the 4th? Because all of our terms are how compared to 1 over 3k to the 4th? They're all smaller. Is that right? Bryce is giving me the look. What's the look for, Bryce? They're subtracting, so the denominator is? The denominator is smaller. So all these terms are bigger. You see? The denominator is smaller than what I've circled in blue. Or, I'm sorry, the denominator gets smaller because we're subtracting. But the whole fraction then, those fractions, those terms are all bigger than 1 over 3k to the 4th. Do you see it? Does that make sense? Making a denominator smaller makes the whole fraction bigger. So now I've got this series that converges, and all my terms are bigger than the series that converges. Conclusion. You can't make a conclusion, right? So good. So I've got a series that converges, and I got a bunch of terms that are bigger. That may converge or it may diverge. Don't know. So we can't use direct comparison for this, but what we can do is we can say, what does this sequence essentially become in the long run? Okay, so in the long run, when k gets really, really big, all these terms are going to be, yes, really, really close to 0, but more specifically, they're going to be really, really close to what? 1 over 3k to the 4th, right? Okay, so for really, really big k, so this is kind of when you did your rational functions in pre-calculus, so when k gets really, really large, like 1 billion, well, this is 1 billion to the 3rd, but this is 1 billion to the 4th. So this is 1 billion times greater than that. And take it to 100 trillionth. If you got 100 trillion to the 3rd and 100 trillion to the 4th, how do they compare? This one is 100 trillion times as big as that. So for really, really large k, this fraction essentially becomes 1 over 3k to the 4th. And the series 1 over 3k to the 4th converges or diverges? Converges. Okay, so this is kind of like indirect comparison. So we can't use direct comparison. We can't say that we know that those terms are actually a little bit bigger than 1 over 3k to the 4th. But we can look in the long run and say, what does this essentially become? It essentially becomes 1 over 3k to the 4th, which converges, so we can conclude that that converges. Okay? So subtle difference, right? So what you have to know about that is, yes, you look at that and you say 1 over 3k to the 4th. This is gonna converge because that's essentially a p series, but not by direct comparison, because actually these are all a little bit bigger than 1 over 3k to the 4th, but by kind of long run comparison, right? Long run equivalence to 1 over 3k to the 4th. Questions on that? Yeah, please.
So anytime you have a polynomial in the denominator, you just look at the greatest power. Everything else is just going to become irrelevant at that.
Yeah, so we didn't have to do that here, because this one was a little bit easier. So we just said, oh, all these terms are smaller than 1 over I cubed. Done. But in this case, when we can't do that direct comparison, because all these terms are a little bit bigger than 1 over 3k to the 4th, now we need some different reasoning. And that's where you let k get big, and you say it's like 1 over 3k to the 4th. So it's difference in your reasoning, but the conclusion ends up being the same. Okay, other questions? Yeah?
If we were to add k cubed minus k, would that make any difference?
Plus k cubed minus k. Yeah, so yes, then you could do direct comparison, because k cubed minus k will always be positive. Then you're making the denominator bigger, smaller fraction, direct comparison. Yep. Other questions? Okay. New stuff. Alternating series. We talked about this idea of alternating before. And what is that, just in general, what does that mean, alternating? Plus, minus, plus, minus, plus, minus, right? And that can happen in sequences, but then you also have series if the sequence is alternating. Okay, so an alternating series has terms that alternate between positive and negative. And commonly we'll express it this way. The sum of -1 to the I times the sequence bi, where bi have all positive terms, right? So if bi is all positive, and then you put this -1 to the I along with it, then it takes that positive sequence and makes it alternate. So oftentimes we'll express alternating series this way. So you've got this positive sequence, and then this -1 to the I that makes the signs flip back and forth. Okay, so see if you can do this. I want you to write the alternating harmonic series, both with sigma notation and for a third grader. And we want to make sure the first term is positive, right? What is the first term in the alternating series? Or sorry, in the harmonic series? 1, right? 1 over 1. Okay? So we want that one to be positive. So can you write it both ways? Write it in with summation notation and write it for a third grader. Okay, Mark, how did it go? You do either one of those, either as a summation or the meaning? Okay. Okay. Remember the harmonic series? One over I. And why -1 to the I minus 1 and not just -1 to the I? Right, so that's the way that we make sure that first when I equals 1, we get +1. Because
Does it matter if you do I minus 1 or I plus 1?
nope. I think you normally see I minus 1 more often, but it does not matter at all. Yeah, I plus 1 would be fine too. So we just got to offset that I by 1 somehow, and that makes that, when I equals 1, it makes that positive. Okay? Some of you get that? Okay, good. And then what is that? So you should have 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth, etc. Okay, just the plain old harmonic series, converges or diverges? Diverges. It's what kind of series? P series with P equals? That's what the harmonic series is. It's a P series with P equals 1. Diverges. What about the alternating harmonic series? Diverges or converges? What's happening here? We're talking about an infinite sum, and now how is this different than the harmonic series? Yeah, right. So he's talking about the partial sums. Partial sums get larger, but then what? Get smaller by a little bit. Then it gets larger, then it gets smaller. So every other term is subtracted. Is this going to help our cause in convergence? If every other term is subtracted instead of all of them being added, is this going to help our cause? Yeah, hugely, right? Instead of adding up an infinite number of positive values, now half of them are negative, pulling us back, right? subtracting off. This could help hugely. So let's see what happens. So let's write the sequence of partial sums. And I'm going to kind of do it visually here. So what's our first term? First term is 1. So we're at 0. Our first, say we're at 0. So then our first term is 1. That's like A1. And that S1 then is what? This first sequence? First term of the sequence of partial sums? Is 1. Then what's A2? Negative 1/2. So from there, I'm going to go back negative 1/2. So here's A2. A2 is negative 1/2. So what's S2? Positive 1/2, right? It's 1/2 minus 1/2. Now I'm going to do what? Add a third. So what's S3 now? What's my... So that's what? 1/2 plus a third is 5/6. And now what? Now I'm going to subtract a fourth. So my A4 is minus a fourth, making S4 what? Whatever that is, right? S4 is going to be 5/6 minus a fourth. If you know what it is? Anyone know what it is? I don't know. I'm going to write out. But see, here's what you can do. This is just as valid. I can write out 5/6 minus a fourth. Perfectly valid way to write that, right? If I can't figure it out in my head fast. Okay? Then what? What's S5? I'm going to take that number and do what? Add a fifth. So S5 is going to be 5/6 minus a fourth plus a fifth. So what happens? Every partial sum becomes a new bound, right? A new bound. So like it's never going to be less than S4 anymore. And now it's never going to be greater than S5 anymore. And then now S6 is going to be a little bit greater than S4, and it'll never be less than S6. See what's happening? So converge or not? Yeah, the series of partial sums is like honing in on some value between 1/2 and 1. So the series definitely converges. And why? Because it gets all this help from the terms that are now subtracted, right? Instead of adding them all. It gets lots and lots of help, right? So it doesn't even make it past 1, this sum. So it's going to get locked in somewhere here at around 0.6, 0.7, somewhere in there is going to be what this sum converges to. If you just were able to add up all infinitely many terms, you get some number around 0.6 or 0.7. Yeah?
Can we evaluate where that converges to?
No, not what we do in this class. But how can we get a really good approximation? So she says, can we actually get what the sum is? Exactly. No, but how can we get a? I mean, we already have an approximation, right? We already have S5. See, S5 is already an approximation of the whole sum. How can I get a better approximation? Yeah. The further you go down in the sequence of partial sums, the better approximation you get. Every time you take another term in the sequence of partial sums, you get a better approximation. So S100 would probably be a very good approximation for this, I mean, within maybe a couple decimal places. And then S1000 would be even better. So that's what the sequence of partial sums does. It just gives you a better and better approximation for the whole sum, right, as you go from one term to the next. Okay, so now let's talk about the alternating series test. So the alternating series converges if two things. So if you have an alternating series, there's two things that are required for it to converge. First is remember now just BI, those are all positive, right? So remember we like kind of pull it, we take this alternating series and we say let's get just all the positive terms and then put the negative one to the I on it. So when I say we're talking about the B sequence, B is all positive terms. So what does it mean that BI plus 1 is less than or equal to BI? What are we saying about the sequence then? What does that say about the sequence? bi plus 1 is less than or equal to bi. What does that mean about the sequence? Each term compares how to the one before? Smaller. So the sequence is decreasing. These are all positive, right? So the b's are all positive values. Here's where the alternating part comes in here. We're separating out the alternating from all the terms as positive terms. So now we're looking just at the terms as positive terms, and each one is less than the one before. So the whole sequence is decreasing, right? So decreasing or staying, so less than or equal to, right? Decreasing or staying the same as the one before. All right, so that's the first condition. As long as the positive terms are decreasing, and also that the limit of those terms is 0. So put those things together, and we say that you look at the positive terms of the, sorry, I shouldn't say it that way, because it's not like we're looking at every other term, right? We know every other term is positive and every other term is negative. We're looking at all the terms in their positive form, right? All the terms in their positive form, what do they have to do? They have to decrease, and they have to decrease to 0. And as long as they're decreasing and decreasing to 0, then the series converges. Now, that's a lot like a concept we talked about earlier. We said that, what? In order for a series to converge, the sequence had to converge to 0. But was that enough? No, that wasn't enough. But if you now make that alternating, it's enough. You see? As long as your series sequence goes to 0, put alternating on it, it will always converge. So, Caden, yeah.
Yeah, does it matter if in this example, we want the first one to be positive, and that's why it's -1 to the I minus 1? If it was just -1 to the I, does it still converge?
Yeah. It's just that your first one goes below.
So your answer's going to be negative.
Could be. It could be negative. Yeah, because it has to be. Yeah, it would have to be. Yep. Okay, so you see this? So this was a big theme we had at the beginning of the series stuff. This big theme was, if the sequence converges to 0, then the series may or may not converge, right? And that was required for a series to converge, is the sequence went to 0. And then we said, well, the jury is still out, all right? Well, now, in an alternating series, if that sequence goes to 0, it does converge. You can conclude it converges always because of the alternating effect. So does that make sense? All right, so I've got a couple for you here, relative to natural log function. So here's -1 to the I minus 1, ln of quantity 1 over I, and -1 to the I minus 1, 1 over ln of I. So I'm going to remind you of what natural log, what its behavior is. Here's natural log. So solving these is going to be a combination of understanding natural log, reasoning, applying the facts that you've memorized about, especially maybe the alternating series test, because these are alternating series, right? Maybe it applies to one or both of these. But you've got to do the analysis, right? So you've got to think through it, talk through it. So I'm going to take attendance and let you work on these two, okay? Combining memorization of facts and making reasoning, making connections, and making conclusions. You got to have both. You got to have both. Go. What's happening here on that first one? Yeah. Okay, how? Okay. Right. Okay. Okay. So, all right. So you're applying this alternating series test. So if if a series doesn't meet the requirements of the alternating series test, does that mean that it diverges? So if it does meet the requirements, we know it converges. But if it doesn't meet the requirements, can we conclude that it diverges? Fortunately, so the alternating series test tells you when an alternating series will converge. It gives you criteria that you can conclude it will converge. So if it doesn't meet the criteria, can we conclude that it diverges? No, right? It may or may not. No, it just doesn't. The alternating series test gives us a criteria that guarantees it converges. So now if you have a series and it doesn't meet the criteria, then can you conclude it diverges? No, it may or may not, right? It doesn't say anything about series that don't meet the criteria. It only says something about series that do meet the criteria. It could converge or diverge. It just doesn't, it's not conclusive. What the alternating series does is it gives you criteria so that you can conclude a certain series is convergent. But if you don't meet the criteria, then you can't, there's no conclusion, right? It's got to do one or the other. So, yeah.
So as 1 over I, or I approaches infinity,
Okay.
1 over I will get closer and closer to 0.
That goes to 0.
And on the natural log graph, that's basically negative infinity.
As 1 over I, so as your argument into natural log gets closer to 0, what does natural log do? Goes to negative infinity.
And so then it would be divergent because each term is going to be bigger than the last.
So what's going on here? What principle are we seeing here? The sequence goes to negative infinity. Divergence test. This is the very first thing we look at, right? If the sequence doesn't go to 0, what do we say? Game over, right? Series can't converge. So that's what we have. This is just seeing that those terms don't go to 0. It goes to negative infinity. So this thing could never converge. Divergence test. The very first test we talked about for series, we said, if the sequence doesn't go to 0, then you just stop. And then there's nothing, you know it will. The only chance a series has to converge is if what? The sequence goes to 0. That's the only chance a series has to converge. If the sequence doesn't go to 0 by the divergence test, the series will not converge. So this really has nothing to do with the fact that it's alternating. It just, you have a series that the sequence that doesn't go to 0. If it doesn't go to 0, series diverges. Okay, what about this one? Yes, sir.
The first term 1 over 0.
For what now?
1 over ln of 1. If I is equal to 1, it would be 1 over 0 for the very first term.
No, it's 1 over 1.
No, the second.
Yeah, I guess so. So let's do n equals 2. So we'll start from 2. Yes, good point. Okay, so if we start from 2, that's a good point. Now, what about this? Yeah. Okay, because? So looking at this right here, we have got an alternating series. He's seeing, does it meet the criteria of their alternating series test? Do those terms decrease? Yeah, because ln is an increasing function. ln is increasing, so 1 over ln is decreasing, and then does that sequence go to 0? Right, yeah, so ln of I just keeps getting larger and larger and larger, so 1 over ln of I will approach 0. We've got both criteria met, and it's alternating. Therefore, converges by alternating series test. Questions on these two examples? Anybody? Okay. So let's talk about something then called absolute convergence. What the heck is this? Absolute convergence. So what do we see with the harmonic series? The harmonic series diverges, but then when you make it alternate, that gives it the help that it needs to converge, right? So absolute convergence, the idea is this. Does it actually require the alternating help in order for it to converge, or does the series converge regardless of whether the terms alternate or not? So the idea here is, does it need those minuses in there to help it converge, or will it converge regardless of their all being positive or half of them being negative? So which one of those two would you call absolute convergence, A or B? B. It converges no matter what, right? So it's absolutely convergent, meaning you can take half of them to be negative or not, and it still converges. That's the idea of absolute convergence. So if B, then the series converges absolutely. So mathematically, what does that mean? It means the series converges absolutely if the series with all positive terms also converges, right? So if any of them were negative to start with, any of the terms were negative to start with, make them all positive, and if that thing still converges, then that original series converges absolutely. Again, it doesn't need the help of alternating series to get it to converge. Then it's absolutely convergent. Now, what if it does need that help? Okay, so if it does need the help, we call that it converges conditionally. Series that converge conditionally, they need the help of every other negative. So it converges when it alternates, but it's not absolutely convergent. If it doesn't alternate, it won't converge. So that's exact. So the alternating harmonic series is a perfect example of one that converges conditionally, right? The alternating harmonic series, because it converges, but then if you make them all positive, you got the harmonic series that does not converge. So the alternating harmonic series is not absolutely convergent. It's conditionally convergent because it needs the alternating help. All right, so let's talk about alternating P series. An alternating P series would be, we got our standard P series, and we make it alternate there. Here I use J plus 1 for our alternating term. You guys asked about that. So for what values of P does the series converge absolutely? Meaning, take away the alternating effect and it still converges. So for what values of P will it converge absolutely? He wants P greater than 1. Agree with that? Yeah, that's what we said. Before we talked about these making it alternate, we said the P series converges when this thing converges if P is greater than 1. So it's certainly also going to converge if you make it alternating, right? But the fact is, if it's not alternating, it still converges, and that's when P is greater than 1. So what about conditionally? So when will it? When will the alternating P series converge conditionally? P is equal to 1. What about when P is less than 1? Diverges? All right, I have some examples down here. So this one, negative 1 to the j plus 1 times 1 over j to the 4th. Is that absolutely convergent, conditionally convergent, or divergent? Absolutely, conditionally, or diverges? Absolutely convergent, right? It does not need that help of the alternating terms to converge. Okay, now what about this? So what's the value of P for this one? P equals 1/3. Is it absolutely convergent? Is it conditionally convergent, or is it divergent? Well, what do we have to figure it out? What tool do we have to figure this out? Not comparison tests. What kind of series is it? Alternating series. Do we have any tests for alternating series? The alternating series test. The alternating series test. What does it say? Alternating series test. Does this thing, do these terms decrease to 0, right? First condition, positive terms are decreasing. Second condition, does that thing approach 0? Yes or no? Do these terms? That goes back to our P sequence. When does a P sequence converge to 0? When? Sorry, I. Greater than 0, remember that. So the sequence, all you need is a positive exponent. And that thing gets really big, and the whole fraction goes to 0. Remember that? When P is greater than 0. That was our P sequence, right? It was the first thing we talked about, was first type of sequence we talked about. So as this sequence, as I gets large, does this sequence decrease to 0? Yes. Therefore, so it converges. Is it absolutely convergent or conditionally convergent? Conditionally convergent. So it, by the alternating series test, converges. All right? But just 1 over j to the 1/3, meaning take all the absolute value of all those terms, does that converge or diverge? That diverges, right? When P is less than 1, the P series diverges. So the overall conclusion about this original series is conditionally converges. Did I lose you? That's right. That's right. So conditionally would be P between, so greater than 0 and less than or equal to 1. That's right. Yep. So all the way to 1, and then any positive value less than 1, it's going to converge conditionally.